So we talk about cohomology of discrete topological module. Topological groups and discrete topological modules. We finally apply the above machinery. The above machinery is about show the exact sequence, to line exact sequence, something like that. In the case of cohomology of groups, we begin with some definition. A topological group is a topological space equipped by a structural group such that the functions multiplication and inverse are continuous. Morphisms of topological groups are continuous group morphisms. So it's continuous as topological space and also group morphism. We denote this category by this. We remark that the category of groups is a full subcategory of topological groups. Is a full subcategory of the category of topological groups. The functor is given by putting on any abstract group the discrete topology. And the abstract group G, it gives the discrete topology. It becomes a topological group. Any point, any element of this group is the open subset of this topological group. Because this is a subcategory of the category of topological groups, and is full subcategory, it means that the homomorphism as a group is bijective with homomorphism as topological group. Since homomorphism of the category topological groups, it has to be a group homomorphism first, but then more condition to be continuous as topological space. But here, when you put the discrete topology, any group homomorphism is continuous. So it's a full subcategory. We will use the following facts about topological groups whose proof is an exercise. The first one is the multiplication. So the lecture notes I'm using is from Professor Tossici. This is his lecture notes for his lecture. I just took it and studied it. So we will use the following facts about topological groups whose proof is exercise. The first is the multiplication by element of the group is homomorphism. Okay? Element of the group multiplication. Therefore, we can always reduce to work on a neighborhood of the identity element. All points are topologically equal. All points are topologically equal because of the extra group structuring. So it's symmetry. This group gives you symmetry information. We are working on a topological space. Not any points are topologically equal. But when you're working on topological group, any points are topologically equal. Starting from a point G1 by multiplication by G2, G1 minus you come into the neighborhood of G2. And this map is continuous and a group homomorphism. This is a homomorphism. Multiplication by element. This is not the right way. Multiplication by element. For example, multiplication on the left. So this maps G1 to G2 and the neighborhood of G1 to neighborhood of G2. Any open subgroup is closed. Any open subgroup is closed. This is what we know, because a subgroup is open if and only if it has finite index and a subgroup. A subgroup is closed if and only if it has no restriction on the index actually. Okay. Now what I mean is, if you start with an open subgroup, then it's closed. But you start with a closed subgroup, it is open when the index is finite. Okay. Of course, not any subgroup is open or closed. We don't know this. Okay. We see a closed subgroup is open when it's finite index, and an open subgroup is always closed. So at the beginning I say something wrong. Okay. It's just because you start with an open subgroup, you write the whole space as the union of the coset of this subgroup. Thence multiplication by element is a homomorphism. So if this subgroup is open, all its cosets are open. So this is the complementary of the union of its cosets except itself. So it's a complement of union of open, so it's closed. On the other direction, you start with closed. The problem is it is complement of a union of closed. A union of closed is not closed unless they're finite union. So you start with a closed subgroup. You want to go to an open subgroup, it must be finite index. Third one is a subgroup of a compact group is open if and only if it is closed at a finite index. Okay. Topological group is Hausdorff if and only if the identity element is closed point. This is what we know. The topological group is Hausdorff if and only if the identity element is a closed point. Yes, this is what we know. A subgroup of a topological group is open if and only if it contains an open set containing the identity. This says you have subgroup. Is it open? It is, if it contains an open set containing the identity. If you have an open inside this subgroup, then this is an open subgroup. You see, there is some connection with this 2 and 3. Well, we see an open is closed, but we don't know if a closed is open. We see a closed will be open if it's sub finite index, but it doesn't mean that it is closed. It is open if and only if it is closed at the finite index. So you see, we can only see this when it's compact group. A subgroup of compact group, you know it is open if and only if it is closed as finite index. The problem is, you start with closed, You don't know whether it's open, but you know it when it's finite index, it is open. But it doesn't mean that when it's not finite index, it is not open. We don't know that. But here in the compact group case, you know that there is an if and only if. So what happened here in the compact group case? We start from closed, which is closed as subgroup in G. Then the whole group G is a union of its cosets. If H is open, then all the cosets are open. So you write G as a union of disjoint open infinitely many. This contradicts that this is a compact group, which means any open covering has a finite subcover, but you don't have because these cosets are all disjoint. Okay, this is okay. And let's say the final one. If and only if a subgroup is open, if and only if it contains an open set containing the identity subgroup. Okay, this direction is obvious because itself contains the identity is a subgroup. The other direction, if it contains a subset of identity, open subset of identity. There is open subset of identity, and you are a subgroup containing it. Then I claim you are open subgroup. You see, for any element of this group G, if it's already in this open set, then it's okay. Can you find any element of the G that is not contained in this open containing identity? If you cannot find it, it means this G is this open subset containing identity. Then it is group and it's open group. If not, then you can find an element G that is in this subgroup but not in this open set containing identity. Then you multiply this element with all the elements of this open, and this is again an open, because multiplication by element is continuous map. And yes, it's continuous map. It's by our definition. Okay, function multiplication, the inverse are continuous. So this is again open. By doing this, you can cover the whole group. It's never jumping out because you're doing multiplication inside the group. So you can write in your element, your group G as union of GI times this open set with identity. So it's open, okay? That's how easy exercise is. Let's move on. Definition. A GB topological group. So here is the important thing. What is G module? We talk about Galois cohomology, the computing, the Galois cohomology, acting on the resolution of a G module. So write exact sequence of G module. The computing is the fixing point functor is left exact functor. After that, you compute the cohomology. Okay, that's what happened later, man. But a G module is discrete. Well, here you see it requires discrete. Sometimes it's not discrete, in fact, but here is easy case discrete. Abelian topological group. So it's discrete, it's abelian, and it's topological group. So we call it a module, it's topological group. Okay, it's a group endowed by continuous section G. require this continuous action. How to interpret this continuous action? It means that there is group homomorphism or rigid automorphism. Where on the second set, the law group is given by composition. The group law is given by composition such that the induced function is continuous. A morphism of G modules is a morphism group compatible with the G action. We all know denoted G mod, the category of G modules. And by home G Mn, the group of G morphisms between G module M and N. Here's the lemma. A GB topological group which acts on discrete topological group H. The following statements are equivalent. The first one is the action is continuous. The second is the stabilizer of any point is open. The third is we can write this topological group, discrete topological group, as the union of the fixing point of H of itself by subgroup of the group G. Okay, this tells you when is a discrete abelian topological group G endowed with a continuous action. When do you have a continuous action? How do you check it? You can check it whether the stabilizer of any point is open, or whether this module, or whether this topological group can be written as the union of fixing point of itself by the open of this group G. This one is not very difficult. We'll jump this. We'll go on to the definition here. Here we define this group of algebra. A GB abstract group and RB ring. We define RG as the ring with elements as finite formal sums. Finite formal sums. Where almost all the AG 0. The sum is given by you adding the position corresponding to the same element of G together, and the multiplication is by your multiplication all those coefficients whose you see the coefficient is indexed by the element. So the coefficient of G is indexed by G. So we do the multiplication. What is the coefficient of element G? That is the multiplication of the coefficient of those elements whose multiplication is G. So if there is H1 L1 multiplication equals G and H2 L2 multiplication equals G, and that's the only two cases if whose multiplication is G in choosing one term from each of those two brackets, then the coefficient is the summation of H1 AL1 and H2 AL2. It's like this, okay? It's like group algebra, okay? Remark that RG as group is a free abelian product of copies of R. If you just regard it as group, it's not only a group because you have a multiplication, but only if you as a group, so you only consider the multiplication. It is a free abelian product of copies of R, Okay, this G is just fixing a position. So there are G positions in this group. Each position you do the multiplication, you do the summation in R. So it's just okay. In fact, it is a free R module. Let G be a discrete group. Prove that it is a ring. Let's do this exercise. Or prove what is a ring. I guess you can prove for any ring R, this group ring is a ring, of course. Prove that the category of the G module. This is a ring, okay? Reasonably, he said the G. The category of the G module is equivalent to the category of a G module. So you want to say this category are equivalent, you have to construct a functor. So the G module is a ring, so it's the Eurofence. G module has a discrete abelian group. Discrete abelian group is continuous action. So here the G module M is a group, abelian group, and we can do it with discrete topology. Here we don't have topology, of course. We're sending it to plus the discrete topology. Okay, so this is abelian group plus discrete topology, and this is the G module, which, wow, how can you make sure this is continuous? The first question. The second one is, well, the second question is, how do you coming back? Okay, let's just do it precisely. You see, the problem with continuous is not a problem because here G is discrete topology, so nothing to worry here. So you have to prove it's fully faithful and essentially surjective. Okay. Why the G module? Okay. Why the G module? Because you have to make it a ring. Okay. The G module. The difference with the G module, and if you want to just ignore these other multiplication map, let's write it more explicitly. For example, mg times mg2, we want acting on m, it should be equal to mg1 mg2 this one is fixing the point E. just like this. Well, actually, this Z module doesn't give you much more information. It's just telling you this. M is a Z module subunit group. Okay, that's it. It's a subunit group. Just n1 times identity of G plus n2 times identity of G acting on G. It is n1 plus n2 identity of G. I am sorry. This also equals n1 identity G, yeah, n2 identity G, yeah. There's a summation. So as a Z module, it is the abelian group, and moreover, it is also G module for the multiplication structure on G. So it becomes a ZG module. Well, this is a very general argument. It's not something special. If you are G module and you are R module, you are also RG module as group algebra. Just translation the operation step by step on this RG module. To be more precise, you see, if you are G module, since you are abelian group, of course you have an action of G on it and have an action of Z on it. So we come a little back. You formally define element of this group ring as this, then you took a G module here. Can you see how do you have an action of this formal sum on M? Surely you have. You just first you acting this element of G as G module on M. After that, this is just the integer, in your case a G. You just do it as abelian group on GM by sum 8 AG times. So this is well defined and making sense. So all you have to check is that the multiplication of this element acting on element M, when you first acting this finite sum on M, after that you acting this finite sum on the result, it's the same as you acting this term on M. That's all you have to check. And also for summation, the same thing you have to check. You first do this summation acting on M. After that, you plus this summation on M. Adding them together is the same thing as you do this acting on M. All you have to check, it's obvious and easy. Okay. So obvious there is a factor backwards. You have to check it's fully faithful and essentially surjective. And the morphism are obvious. Here the morphism are ZG linear morphism of modi. Here the morphism are homomorphism of this category, as we described before. So there is natural factor distraction and backwards. You have only to check is essentially surjective and fully faithful. And in the third case, we compute explicitly this example. In this case, it's just the same as this ring. Say t quotient by t to the power n minus 1. Though in this case, this discrete group G is G. I mean, this case is this one. Okay. If G is D, what is it? It should be ZT. Okay. By the above exercise, we have that G module is an abelian category with enough injective and projectives if G is a discrete group, because in this case it is just a real module of algebra. We know the category of module has enough injective and projectives, so if G is discrete group, category G module has enough injective and surjective, which will help us to do the computation of cohomology by giving us nice resolution. So we say this lemma that G be a topological group, then the category of G module has enough injective. In this case, we are dealing with the general case of G be a topological group, not necessarily required to be discrete. So as a remark above, we already know the case when G is discrete, but we deduce the general statement from this one. After this, we prove the lemma, which states that the application sending a G module M to the fixing point of M by G from the category of G modules to category of abelian groups is a left exact point. After all these steps, we can begin to define what is the group cohomology, the right derived functor of the functor of fixed point.